Alright, so this video is going to be kind of two parts. You're going to have to hit pause when I ask you to hit pause to do a little work and submit on Canvas before you come back. Here's how this works. We're about to move into this world of, so we've been doing multivariable functions, we did a little piece on vectors, and now we're going to move into partial derivatives. Now what the heck do we mean by all that? Here's what I like to do. I'm going to give you like the 3-minute, 4-minute crash course on how derivatives work back in single variable Calc 1 type functions. When I'm done, I want you to hit pause on this video, and I want you to think, how would the conversation sound in a Calc 3 multivariable, let's just go 3-dimensional, 2-variable world? So here comes the crash course of Calc 1. Think about how might this be extended to a Calc 3 world. All right, here we go. 3-4 minutes on my mark and set, go. Back in Calc 1, we would have said this. Given any function, this thing right here just represents any function of x. We want to determine the slope of this curve, the instantaneous rate of the change of this curve at any value of x that we pick. I've just chosen to think about this value of x right here. And here's how we did it back in Calc 1. We said, well, let's first of all change x by a little bit, an infinitesimal amount. Just a small change in x. Now I know for the purpose of my whiteboard here and for my conversation, I've made that change in x kind of big. But I hope you know from Calc 1 that we're talking about infinitesimal changes in x. That infinitesimal change in x was sometimes called delta x. So I'm going to move over a distance called delta x. And at that new input value, we're going to find a new output value. And that new output value, this distance right here, would be called f of x plus delta x, where this input value here, output value here would have just been f of x. So for some x input, there's an output of f of x. For some x plus delta x input, there's an output of f of x plus delta x. So then what we did is we said, let's find the average rate of change between these 2 points. Let's find the slope of the curve, or the average rate between those 2 points. So we would have said, how does this vertical quantity change? Well, look at this. This entire length is f of x plus delta x. This entire length is f of x. Subtracting them gives me the resulting change in that output quantity. So f of x plus delta x minus f of x tells me by how much did my function change by because I changed x by a little bit, called delta x. Dividing that by delta x, sort of that vertical change relative to ratio to that horizontal change, rise over run is how some people remember it, gives us the slope between those 2 points. Now we call that the slope of the secant line. Now can you imagine, we'd allow delta x to get smaller and smaller and smaller and smaller, infinitesimally small. And the way we communicated that in calculus is we said, take the limit as delta x approaches 0. And when we do that, that slope of the secant line between the 2 points, as delta x gets smaller, this point gets closer, closer, and closer, and closer to this point. The slope of that secant line approaches the slope of the tangent line right at that point. And we say with that infinitesimal imagination of delta x being really, really close to 0, we imagine the slope of the secant line, slope of the tangent line. We imagine the slope of the curve, and we say what we're computing with this thing is the instantaneous rate of change, the derivative. And we give it a name, or the symbol, we say f prime of x, or we say df dx, change delta f, delta x, changing the function value relative to changes in x, df dx. If you want to go, we'll talk about the distinguishing characteristics of these two things later, but one of those two symbolisms is they're usually used. Pause. Hit pause on your computer, and now what I'd like you to do is, if you were going to give a similar crash course in just a couple of minutes on what it would look like in a Calc 3 world, what would it sound like? Hit pause, try. Now here's what I'd like you to do. Whatever you try, sketch out some things, draw some things, write some things, and then either take a picture if you've got an app on your phone that allows you to basically scan and turn into a PDF. That's the best way to go if you can, please. There's lots of free apps that do that. Turn your picture into a PDF and send it in through Canvas on that module so I can see what was your initial thinking. Now, if you'd work together on this, fine, but just all of you do it so I know that everybody has participated in sending something in. Thank you. I'm assuming you've paused, you've worked, you've now submitted something. Now here's often the dilemma that people face in this situation. They go, all right, now imagine we have a 3D surface in space, and instead of finding the slope of that tangent line, we're now going to find the slope of the tangent plane. And so we now again need to get things closer together, infinitesimally small changes, but we kind of recognize that we now have a two-variable, multi-dimensional, three-dimensional function here. And so people often think, well, what we need to do is we need to change x by a little bit, and we need to change y by a little bit. If we change x by a little bit, we change y by a little bit, we get a new output, a new function value, a new z value, if you will, but be flexible on all your letter names, right? A new output value. Take that new output value and compare it to the original one just to see by how much did our outputs change by, just like over here. But then what? Divide by what? Over here we divided by that change in x to get that horizontal change, that change in that horizontal distance. But what are you going to do here? Are you going to divide by delta x times delta y? Are you going to divide by delta x plus delta y? Are you going to, what? What happens here? And this is where I'm going to assume whatever you've sent in, unless you cheated and looked, you probably struggled with, all right, I'm going to change both x and y and see how does the output change in that new the z value compared to the original z value, but divide by what? Well, because of that exact dilemma, it's actually not what we do. What we do in Calc 3, and this is why we call them partial derivatives, is we only change one independent quantity at a time. That is, we first of all think about just changing x and leaving y alone. Imagine that. If you just change x but don't change y and compare that to the original's output value, the original z value, to see by how much did the z value change. It's kind of like this. Because we changed x by a little bit, the output quantity changed, and we want to know by how much. Because we changed x by a little bit, the function value changed, and we want to know by how much. And then we, just like over there, divide that by that delta x to see the new, to see the rate at which that's changing. And when you do that for really small changes in x, that is, if you now take the limit as that delta x approaches 0, leaving y the same, leaving y constant, you find out what's called a partial derivative. And this partial derivative is just the changes in our output quantity relative to changes in x. Now notice over here, the Greek letter D is used rather than the English D. And all that does for us in mathematics is kind of gives us a context. Instead of a single variable situation like we had here, we now have a multi-variable context. If you look in your book, in this section, you'll see the nice version of that delta f, delta x. Now we also sometimes say this. Now in the multivariable world, there's no primes. It's just a subscripted x. And what this means for us, because we know what we're talking about now, is how does that function change relative to changes in x only, meaning y is being held constant. Now likewise, we could leave x alone and change y only. Compare that to the original output value as if nothing had changed. And, change y only, and then divide that by changes in y to figure out the rate at which the output quantities are changing because of those changes in y. And again, we do that for infinitesimally small changes in y, and what we get are changes in the function value relative to changes in y, or the partial derivative of the function with respect to y. We call them partial derivatives, partial in the sense that we're holding one quantity constant, y, and allowing just x to change by a little bit, or we're holding x constant and allowing y to change just by a little bit. So we're only computing changes in z relative to changes in y, or changes in z relative to changes in x. Partial derivatives.